Sorry, I'll repeat some of that, but I'll try to go more quickly. I did get pretty much everything on Blackboard updated. Your syllabus, updated syllabus, is out there under, when you go to the home page for this course, in the top group of blue tabs on the left-hand side, you'll see one that says syllabus and book information. Click on that and you'll see the syllabus there. Right below that is instructor information and something, and that's where you find my locator card. And the second group of those blue tabs is one that says handouts, PPTs, PowerPoint points, and more, and that's where you'll find the instructions for the research paper, which we went over last time, but I've updated that file. All the PowerPoints, and there are a ton and a half of those there, more than we'll ever cover in the course. And then there will be the YouTube video link. And again, I'll remind you on the YouTube videos, when you do click on that, the ones at the top are from last term, and the ones at the very bottom are from this term, which right now is only one. After today's class, there'll be two there. And then anytime we cover material that has already been covered, that were covered last time, I'll delete the one from last time, and it'll just be at the bottom. Okay. And then some websites that either I found or students have found and said they found helpful. Slater, Prof. Rob Bob, Education Portal, variety like that, something like that. Okay, so that's all out there. Blackboard is pretty much up to date now. Any questions on Blackboard? Okay, what I need to get from you, because I've taught probably, I don't know how many classes since we last meet, and I can't keep straight who's done what. I know we went over the syllabus and we finished that, right? Any questions on the syllabus? Okay. I think we finished talking about the research paper, didn't we? Okay, any questions on the research paper? Any? Okay. Then I think we talked about my locator card. Does anyone need to see that? See when I'm in class, off campus, on campus, that kind of stuff. If you need to see it, I can pull that up. Anyone need to see that? It's out there on Blackboard. Okay, so I went over that. Did I get to safety? Did I hit all three issues of safety? Okay. Did we get started in 8.3? We did not get started at all. So that's where we left off. That's where we are now then. So let's pull up 8.3. And we'll try to go quickly through this because this is stuff that really should have been picked up in Cal 2, but last term's class we got started. Well, it was my first time through the book, and I got bogged down earlier, and it just has carried through, so we're trying to catch up from the bog down. Okay. Now I have that I'll just pretend we haven't even got there. Okay, chapter 8, well, maybe we'll even turn on projection today. What do you think? Can y'all use projection? Okay, you won't be too scared of it or anything. Okay. It should come out in a year or two. Okay. Well, let me get the slideshow set up then from the current slide. And as soon as the projection starts, sorry, I forgot it, we'll be red-eyed to go. Okay. All right. Now, some of you were not in my class last time. Most of you were. You were not, right? Okay. Did you get into chapter 8 in Cal 2, or do you remember? Huh? Okay. We got started in chapter 8, integration techniques and improper integrals. We did integration by parts. Okay. Do you remember that? Okay, you've done that. Okay, so where we're picking up now is 8.3, which is trigonometric integrals. Did y'all do that, or do you remember? Okay. So we're all basically starting on the same page. So objectives here are to solve trigonometric integrals involving powers of sines and cosines. Okay? We'll solve some trigonometric integrals involving powers of secants and tangent. And we'll solve trigonometric integrals involving sine, cosine products. Okay. Now, some of this you may remember from things being introduced in trig class, pre-calculus trigonometry, especially when you get to the product type stuff. The other things we'll be using trig, of course, stuff with all this. But let's see what these are. Integrals involving powers of sine and cosine. In this section, you'll study techniques for evaluating integrals of this form. The integral of sine m to the mth x times cosine to the nth x, these are powers, or, and in the next section, secant mx tangent mx. Okay. Now you might say, why are cosines, cosecants, and cotangents not being mentioned? Well, you can almost, use those in combinations of these two. These are the most common, okay? Where either m or n is a positive, integer. I don't like the way that's stated. I think they mean both m and n are positive integers. I can't think when we'll ever put any of those as negatives. Okay? Because if m was negative, you'd write this as a cosecant. So I think they both have to be positive. I can't think of a good counterexample, but I believe they will be positive integers. To find antiderivatives for these forms, try to break them into combinations of trigonometric integrals to which you can apply the power rule. There's the key. Okay. Now, I want someone to remind me, what is the relationship between sines and cosines, especially in terms of antiderivatives, which would be related to derivatives. What is the relationship between sine and cosine? Yeah. Derivative of sine is cosine, and derivative of cosine is sine, negative sine. Which means the antiderivative of sine is negative cosine, the antiderivative of cosine is sine. Okay? But we've got these powers in here, so they're going to mess up things a little bit. Let's go over here to secants and tangents. Any relationship there? It's hard. Trying to think back that far. Any relationship?
1 over tangent? Isn't that secant? Or 1
No, that's cotangent. Okay. All right. How about this? What is the derivative of tangent?
Secant squared.
Secant squared. And derivative of secant? Say again? Secant tangent. Exactly. So, hey, depending on those powers and things to do with the powers, especially, okay, let's go back and see another relationship. This one not to do with derivatives and antiderivatives between sine and cosine. Can you remember any special relationship there?
Sine over cosine equals tangent.
Say again?
Sine over cosine equals tangent.
Okay, that is, but let's not get those. Let's just leave it sines and cosines. That is what I call a ratio or quotient identity. This is one of the identities, but not that one. This one is when you have powers.
Sine squared plus cosine squared equals 1.
Yes, okay. So anytime that you have an even power for either one of these, you can then express that as 1 minus the other one, not to that same power, but you can fiddle with it. So let's put it that way. How about these two, secants and tangent? Say that again.
Is it 1 minus tangent is the equal to secant or something like that? I forgot that.
It's something like that, I guess. Okay, but not that. Anyone remember? Okay. A relationship between secants and tangents in terms of identities. And specifically, the identity we just used here, what do we call that identity? Sine squared plus cosine squared is equal to 1. Oh, most famous theorem in geometry and trigonometry. He led a group of guys out into the thing and they studied numbers all the time.
Sounds like a cult.
Huh?
It sounds like a cult.
It almost was. I can't believe that none of you have written a paper on him. Because it seems like half the papers I read are about him. Science, A squared plus B squared equals C squared. Pythagorean identities. Okay? It's exactly where you got this one and that one. What's the Pythagorean identity that relates secants and tangents? Okay. I'm not much one on memorizing. So here's what I do. I do remember this one. You've already told it to me, so I'm going to write it down. And this I don't count as memorization because you told it to me. Sine, say that again. Not quite. Yeah, something like that, but not. Close, but quite. Sine squared x plus cosine squared x is equal to 1. Y'all told me that one, right? Now, what happens if I divide every term by cosine squared x? That's legal in most states, right? Say that again. Tangent squared is equal to secant squared. There it is. Okay, so between our derivative and antiderivative relationships and our Pythagorean relationships, we are going to be able to manipulate and come up with things for just about any form we want to there. Okay? So to find the antiderivatives, try to break them into combinations of trigonometric integrals to which you can apply the power rule. That's our goal. Okay? For instance, you can find the integral of sine fifth x times cosine x dx with the power rule, because you're first going to do a, what was the thing we sort of did back in chapter 3? Where was that? Way back. All right. Welcome back. Let me find my roll here. Catherine's here. All right. Even though Charles isn't here now, I have seen Charles today, so everybody has been here today. Perfect attendance, with that little exception there. Okay. Remember, this is the derivative of that. So what manipulation can we apply to this to take advantage of that? Think of it. All right. Looks like you're getting tired out there. You drew your fourth file, so I'm going to substitute. Okay, yeah, have at least one basketball fan. Okay, good. Substitution method. Okay, because let's take the most complicated one, sine. Less, if you want to use your u's, you can. You don't have to. Let u equal sine x, right? Then, what would be the next step? Du is equal to cosine x but you write this as not derivatives but differential, what goes here then? Something goes here. Dx, exactly. All right. Well, now here, cosine x dx, this is your du, right? And sine x was your u, so what do you have here? The integral of u to the fifth du. And guess how you can do that one? The power rule. That's exactly a power rule problem. How would it run? What's the antiderivative of u to the fifth du? U to the 6 over 6. Don't forget this. Indefinite integral. Help me, help me. Oh, it's been a long time. At least a month. Plus c. You always have to have a plus c with an indefinite interval. All right, but we know what u is, don't we? What is u? What are you? No, what? No. What would that be? Sine x. So this will be sine 6x over 6 plus c. And there we have it. Okay? So, really easy if you just have either sine or cosine to the first power. If you have that, it's easy to do these. Because you just take the other one, let that be your u, then your du is going to involve the one that's to the first power, dx. Okay? But life is not always that nice. Yes?
Why is sine more complicated than cosine?
Why is it more complicated?
You said take the most complicated one.
Oh, because it's to the fifth power, that's to the first power. Yeah, that's what I meant. It's bigger. Okay. We won't always use that, but for substitution, that's the one that's what I look at. Okay. Now, what if both of these have powers into them? Well, here's what we look for. We look for either one of these to be odd. If it's odd, ha, we got it. Okay?
So it doesn't matter if it's less than the other.
Second?
It doesn't matter if it's less than the other.
What?
If it's less.
Oh, yeah, it doesn't matter which is greater or less. We look for one to be odd. Okay? Here are the things we were just doing. Sine squared plus cosine squared equal 1. Remember we said that. Which we could write several different ways. Sine squared x is equal 1 minus cosine squared x. Cosine squared x is equal 1 minus sine squared x. Or, then you get your double angle formula. Does anyone remember that? Now notice this is only cosine. Double angle cosine formula. Anyone remember that one? Cosine 2x is equal to, now if you don't remember that one, maybe you remember this, cosine of x plus y. Anyone remember that one? Oh no. Oh boy. All right. Here's
Is the sine equal to 1?
not quite. I know what you're sort of doing down there, but not quite the same. Let's start with this. Cosine of x plus y. See if this rings a bell. Cosine x, cosine y. Anyone remember? Minus sine x, sine y. Sorry, I ran out of room there. Okay, y'all don't remember that one. Okay, that's the sum angle formula for cosine. There's one for sine too, we're not going to be using that here. There's one for tangent, we're not going to use that here. The cosine comes into play. And here's why. What if x is equal to y or y is equal to x? Then what we have here is x plus x, which is 2x, right? And let's see what we have there. So the That's what I was going to write here. Cosine 2x would be cosine x, which is cosine squared x, minus sine x, which is sine squared x. Now here's why it's important. That is so close to this one. The only difference is you got a minus here. So if you put these over each other, I'm going to put this one underneath that one. Okay? I'm going to rearrange it a little bit. I'm going to put the 1 over here is equal to cosine squared x plus sine squared x. Right? Isn't that the same as this? It just rearrange the sides and rearrange the order. But it's okay, right? Now let's add these two equations together. Cosine 2x plus 1 is equal to 2 cosine squared x plus 0. So cosine squared x is equal to 1 plus cosine 2x divided by 2. There it is. Now if you subtracted them from each other, let's put this one, imagine it's on top, and subtract that one from it. Then you'd have 1 minus cosine 2x. These would then go to 0 if you're subtracting. And this would be 2 sine squared x divided by 2. Sine squared x is equal to 1 minus cosine 2x. So that's where those two come. Now, this is, of course, your Pythagorean identity. This is a power-reducing formula for sine squared. This is a power-reducing formula for cosine squared. Okay. So, what's the big deal here? Okay. Well, the deal is you're going to use these when both of these m and n are even. If one of them is odd, we can use that. But if both of them are even, we've got to use this. And that's what we're going to get to. Okay. So much esoteric stuff. Let's actually get it. Here's the guidelines for evaluating integrals involving powers of sine and cosine. We're not going to mess with tangent and secant anymore. No, tangent and secant right now. Okay? Sines and cosine. When the power of sine is odd, that's what we're going to look for, and positive, of course, okay? Save one sine factor off by itself and convert the other remaining factors to cosine using the Pythagorean identity. We'll show how to do it in a minute. Then expand and integrate. Okay? Whew. They have to throw in letters here. If k is any integer, 2k plus 1 has to be odd, right? Because 2 times k would be even, add 1 to it would be odd. So this is an odd exponent here. It doesn't matter what cosine is, it can be anything. The n can be even or odd. It doesn't matter, okay? But this is odd. So what we're going to do is take the odd one out, sine x, and put it over here with the dx, right? Sine x dx is the derivative of cosine. Okay. So then what we're left with is sine to the 2k x times cosine nx. And we're not worried with cosine nx just hanging out there. Well, let's take this sine of 2k, sine of 2 raised to the 2kth power, and do it sine squared raised to the kth power. Okay, does that make sense? Okay, because it's now 2k, okay. But sine squared, we know exactly what that is, don't we? Pythagorean identity? 1 minus cosine squared, right? So now you get this in terms of cosine squared, this is in terms of cosine, this is in terms of cosine squared, yeah, and this is in terms of cosine, and this is to the kth power, this is to the nth power. So what we have then, the sine squared is 1 minus cosine squared raised to the kth power times cosine raised to the nth power times sine x dx. Okay? Now, whatever that is, whatever it is, it's all in terms of cosine. So if that k, most of the time we're not going to use too large a k, maybe 3. I doubt if we even get as many as 5. Sometimes just 1, maybe 2, but it's some k, some number, positive number, okay? So you'll just take this and multiply it by itself k times, okay? But like I say, most of the time k is not going to be all that big. All right, and then what we'll have is this multiplied by this would be cosine int x minus cosine whatever this turns out to be plus that. So it's just some power of cosine. And this is the derivative of cosine. So guess what? You use a substitution and you come up with the answer. Okay? We'll do some with problems like this. Hang on. So when the power of cosine though is odd and positive, then do the same thing. Factor out one cosine. So cosine is odd and positive. Cosine 2k plus 1. Whatever your odd number is, take one away from it, and that makes an even number, and 2 times whatever it takes to make that even number. Okay. Take the 1 and put it here with the dx, and that's the derivative of sine. The minus. Okay. No, that is the derivative of sine. This is minus the derivative of cosine. Okay. We'll go back and do that later. Okay. And then this is in terms of sine. And then this, you'll do cosine squared raised to the kth power. And again, you can write that as 1 minus sine squared raised to the kth power. However big k is, multiply it, multiply it, multiply it. You'll get everything in terms of sines. And this is the derivative of sine. So again, substitution will give you the answer. Okay. Now, what if they're both even, but positive, not negative? Then we'll make repeated use of these formulas. Okay? If the sine is even, then we'll break that into sine of 2k, and that would be sine squared raised to the kth power. Sine squared is going to be that. The cosine, break that into cosine of 2l, whatever that happened to be. That would be cosine squared raised to the l power. Well, that would be cosine squared. Okay, and then after a while, you'll get odd powers of cosine. Then you go back to this. Okay, so that's basically what we do when we have sines and cosines. If one or the other, it doesn't matter which. If both are odd, fine, it doesn't matter. I would say take the smaller one, but it doesn't matter. Either one will work, and proceed like that. But if both are even, then we do this once, and then you get all odd powers of cosine. Okay, a lot of blah, blah, blah. Let's actually do one. Ha! Here's one. Does that fit the bill? What would you do first? Oh, no. Second? Second? Take out one of the signs because that's the odd, okay? So this will be the integral of what do you have left if you take one sign out? How many do you have left? 2. Sine squared x. Cosine fourth x, don't mess with that for now. And then the sign that you took out, put with your dx. Sine x dx. Because you know that is related to the derivative of cosine, right? Derivative of cosine is minus sine dx, right? Okay, we'll get back to that in a minute. Okay. Now that we have a sine squared, what do we do with that? Think Pythagorean identity. What is sine squared? 1 minus cosine squared, right? And this is cosine fourth x. And this is, what is that? In terms of cosine. See, this has only cosines, that has only cosines. What is sine x dx in terms of cosine? It's derivative of cosine x, right? Only it's the minus derivative of cosine x. Well, let's just write it down. Okay. We'll come back and do it. Okay. Now, let's just take these two and mix them together. This will be the integral of what? If you multiply these, just these two together, what do you get? Nah, multiply. Cosine fourth x minus, help me. Cosine 6x. Okay, times sine x dx. Okay. Now, since you have everything in terms of cosines except this, and that is the derivative of cosine, what does that set itself up for? Substitution. Okay. Sine had too many files, so we're going to substitute. What would that be? What's your favorite substitution variable? U. Okay, me? No, okay. Let U equal? No, just cosine. Cosine x. Then du is equal to minus what? Sine x dx. Perfect. Okay? So, now notice what I'm going to do here. I'm going to throw his calculator to the floor, or his cell phone, okay, whatever it is. Okay. All right. Now, here's what I'm going to do. To take care of this minus sign, I'm going to switch these two terms. Is that okay? And that will negate, okay? So then what we'll have is the integral, and we're going to switch these two terms, and u is cosine x, so we're going to put this one in front. That would be u to the sixth minus u to the fourth du. Now, was that too much sleight of hand? I feel like I'm doing the shell game here. Did I go too fast and lose you? Okay, that makes sense, doesn't it? We need a minus sign, so what we'll do is just flip these two and make it minus, right? Okay, so that's what we've got. I think that we can do that, can't we? What would that be? Power rule. Help me, somebody. A little louder? Oh, no, don't mess with cosine. Yeah, integrate u to the sixth du. What would that be? Over 7 minus u to the what? Fifth over 5. And then what else do we have? Plus c. Now all we do is plug in what u is. And what is u? Cosine. So this would be, however you want to do it, cosine 7th x over 7 minus cosine 5th x over 5 plus c. And that should be our answer. Oh, yeah, okay. They left the minus 5th in front and plus 7th, 8th. You can do it that way. It's perfectly fine. What they did, when they did this, they put the minus sign outside, which is fine, but left it in this order. And then that gave them a minus out here, u to the 5th over 5, minus this over this, but the minus multiplied through it, flip it back again. So either way you want to do it. I just like to go and get them that way. But their answer is the same as ours. They just write the minus cosine 5th x first and the plus cosine 7th x over 7 second.
When you flipped them, how did it make it u6 positive? How did it make sine x dx positive? When you flipped them?
Okay. All right. Try this on for size. Okay. Minus, because this is a minus du. A minus. I need to get a minus in there. So I'm going to put the minus right here. So minus cosine 4th x plus cosine 6x. Okay? Well, let's distribute the minus sign inside. It'll be minus cosine 4th x minus, that is a minus sign, sorry, I was jumping ahead. That is a minus sign there, I'm sorry. Okay, and minus times minus is plus cosine 6x, right? And then just flip the order, and that's how you got that. This is the same as cosine 6 minus cosine 4, right? Which would be u6 minus u4. When you have a difference, and you put a minus sign in front, you just flip them and lose the minus sign. Way back in algebra, if you had a minus a minus b, that's the same as b minus a. Same type principle. Just because that's minus a minus b, which is plus b, so it's b minus a. So if the minus sign's out front, which is basically what it was, we just flipped them, and that took care of it. That took care of the minus sign. Okay. Does that answer it? Kinda? A little bit? Okay. Okay. They left the minus cosine 5th out front, which is fine. I don't like leading off with the minus, but that's fine. It's legal in most states. Okay, computer algebra system has another way of doing so you can certainly do that if you want to. Why would you even mess with that? It's giving you a different answer saying, is that equivalent? The answer is yes, but why would you do that? But we won't answer that. In example 1, both the powers m and n happen to be positive integers. This strategy will work as long as either m or n is odd and positive. For example, in the next example, for instance, in the next example, the power of cosine is 3, but the power of sine is negative 1/2. Ugh. Okay. It's still doable. Very doable. And by the way, this example 2, oh, wait. Sorry. Let me erase my chicken scratch here and watch how they did it. And I think we've already talked through how they did it, but let's just see. Because you expect to use the power rule with u equal cosine x. Now, why would you expecting that? Because you pick the odd one, the odd exponent, and let that pull out the odd one, the sine x dx. That leaves that being even then. Okay? Say one sine factor to form du and convert the remaining sine factors to cosine, which was pretty easy in this case because you only had 2 left. So this is what we did. We took one of these 3 and put it with the dx and left the other 2 out front. Okay? So that would be sine squared x, cosine 4th x, sine x dx. So one of these went with the dx. Okay? Now, that sine squared, we want in terms of cosine because that's which way we're heading. So that makes it 1 minus cosine squared, because that's what sine squared is, times cosine 4th x times sine x dx. But then you multiply those together, and that's cosine 4th x minus cosine 6th x times sine x dx. So you just distribute the cosine 4th across both of those. Okay? Now we've got everything in terms of cosine except that one single sign, which is the derivative of cosine. Negative, of course. So, they wrote it as 2 integrals, which is perfectly fine. You can just put that into 2 integrals. The first integral minus the second integral. Keeping the sine x dx with both of them. Okay, that's legal in most states. And that makes it minus, and where the minus came from? Because, well, they're looking ahead. I would have already done the substitution. They haven't. Substitution makes it clearer. They just said, we want that to be a minus sine x dx. Why? Well, because when we substitute, you need it to be that way. So to make this a minus, you pull a minus out here. And, of course, to do that to be a minus, that would be change this to a plus out here. Again, to me, this is a backward way of doing it until you see what they're doing. now you do your substitution for that you, oh, goodness, not yet, not yet. Okay, they didn't even do a substitution. They just did it in their head. Let u equal cosine x, and you have u to the fourth du plus integral of u to the sixth du. And then when you do that, you come back to this. If you see it this way and understand it well, go for it. I find most students like to literally do the substitution. Whichever way rocks your boat, go for it. Get the same answer. But that's how they came up with such a weird distribution of it, because they didn't do the substitution like I would have done. All right. We're not going to mess with Wallace yet, okay? This is example 2. Now, Brian, I thought it was Brian. I just want to make sure. When you had Cal 2, did you use this book as well? Or were you in a different book? You didn't use this book. Okay. That's what I was afraid of. Let me tell you a few things about this book. Okay? I don't like the publisher. If it were up to the publisher, I wouldn't use this book. Okay? But the author, Ron Larson, I really like his style. And here's why. You don't have a copy of the book yet, do you? Are you planning to get one, or are you going to stay with the one you have? Okay. If you were going to use your old book, I can help you see what's somewhere, and you can stay with it. But do you even have your old book? Okay, then probably better off. When you get your new one, now this is without doing WebAssign or any of that stuff, which I guess, do some of y'all need that to open your ebooks? I had a student in this morning who was able to get their ebook, and I hadn't given her a WebAssign account yet. Maybe they give you some free days, I don't know. I'll try to get that. Do y'all know if you need it? Seems like last term you needed it, but I don't know if that's still true or not. Well, I'll fiddle with that later. But here's what I like. One of the many things I like about this author. Okay? In this example 2, right down here, powers of cosine odd and positive. And they have a pretty odd-looking integral here. Well, look at this. See LarsonCalculus.com for interactive version of this type of example. There you have a free website. You don't need any code. You don't need anything. You can go to anyone. My wife could go to LarsonCalculus.com and look at it. It may not mean anything to her, but she can do it. It's a website. Just anyone can go there. So example 2, it'll be described in gory detail how you interactive version of how you go about doing this. Okay? Now, let me, oh, by the way, I didn't even notice this. Here someone mentioned the beginning of 8.3. Sheila Scott McIntyre published her first paper on the asymptotic periods of integral functions in 1935. She completed her doctorate work at Aberdeen University, which I think is in Scotland or Canada. I don't remember which. I think it must be Scotland, where she taught. In 1958, she accepted the visiting research fellowship from the University of Cincinnati. Here's someone, a paper. If you're interested in her, you could write your paper on her. Or asymptotic periods of integral functions, or anything such as that. Okay. Here on the next page, which we haven't gotten to here, is John Wallace. You saw his name show up there. And you see LarsonCalculus.com also has more on his biography. So wow, you can get more information at LarsonCalculus.com. Okay. Now, before the period's over, I'm going to make some homework assignments. And then look at 8.3 here. My homework assignments are always going to be like this. It's hard to hold up the book. Do any of the odds 3 through 13, any of the odds 15 to 19, any of the odds 21 to 33, either 35 or 37. You get the idea. Odd numbers. two reasons I assign odd number exercises. One, the answers are in the back of the book for the odd numbers. So if you do your exercise, look in the back, get the right answer, go on to the next. Okay. Second reason, what if you don't get that answer in the back of the book? And you can't figure out how they got that? Okay? Look at the top of this. 8.3 exercise. See calcchat.com for tutorial help and worked out solutions for the odd number exercises. So that's what I do. If you can't get that answer in the back, you don't have to wait till the next class and ask me how to do that problem. You can go to calcchat.com. Another absolutely free website. You don't need any codes. You don't need anything to go there. Go to calcchat.com. You'll have to learn to manipulate the website. Y'all are used to that. Y'all are young. I'm a dinosaur. It'll take me longer, but I can still do it. And you can see tutorial help and a worked out solution for every odd exercise here. Okay? Now, not only that. In this first group of problems, remember I said 3 through 13, here number 7 is in red. The number 7 is red. What that means, the red exercises, you can go to another website, and this is called calcview.com. And they will work number 7 in gory detail. I mean, just showing every step. So a lot more information, interactive. Okay? So that's for that. Now, if you happen to notice, every section that has a red number also has one of these QR codes. Y'all know what those are, right? Yay or nay? Okay? If you got a cell phone, a smartphone, you can take that picture, it takes you right to that website. Right there on your cell phone. No, to me, it's hard to see. But it takes you right there. You don't have to type in anything. It takes you there. And you can see their worked out illustration of that example. So, wow. All that's here, free with the book. You don't need WebAssign or anything else. You've got all sorts of tutorial help right here. That's why I don't like using WebAssign. To me, it's kind of awkward. Okay. So, they didn't have example 2, so let's us do example 2. So let's go back. Since you were kind of new to the class, I wanted you to know what all the rest of them knew already. Here's your function. This is example 2. The integral from pi 6 to pi thirds of cosine cubed x over the square root of sine x dx. Okay. Now, the others who've been in my class, I think you know almost what I'm going to ask now. Are you willing to integrate it in this form? Is this a form you like?
No.
Why not? Okay, it has a radical in it. That's one thing. And it has a denominator in it. That's two things I don't like about it. So I always get anything that has radicals in it. How do I deal with a radical? Write it as a fractional exponent, right? What would the square root of x, sine x be? To the 1/2 power. And if it's in the denominator, that would be sine x to the negative 1/2 power. So I don't like them in the denominators. I don't like them in radicals. So I get everything in power form where you can use negative powers or fractional powers or both, like this. So what would this be then? Rewriting this will be the integral from pi 6 to pi thirds of cosine cubed x sine to the negative what? 1/2 x dx. Okay. Now I've got it in a form I like better. Sure, messy, fractional, negative exponents. We can deal with those later. So again, take out a cosine x. You're absolutely right, because that's an odd power. So this will be the integral from pi 6, I can't write, to pi thirds of cosine squared x sine to the negative 1/2 x, and then that cosine I took out, I put with the dx. Cosine x dx. Going to leave that together as a group. Now, that actually looks messier. Yes, because of Pythagorean identity, we can write that as the integral from pi 6 to pi thirds of 1 minus sine squared x, Pythagorean identity, times sine to the negative 1/2 x. The x doesn't go up there. I get carried away sometimes. Clark said I need to be carried away, didn't you? I heard that, okay. Times cosine x dx. Okay? Now what? I'm carrying this out, drawing out in gory detail here. Not yet. Let's multiply first. Well, like I said, I'm carrying out in gory detail. So 1 times sine to the minus 1/2 x is sine to the minus 1/2 x minus, and what's sine squared times sine to the minus 1/2 x? Sine squared x and sine to the minus 1/2 x. What would that be? Sine of, and you say 1.5 x, so let's write that as 3/2 x. Is that okay? 1.5, 3/2. Okay. X dx. Oops, 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 oops. You just about let me mess it up. I forgot my cosine x dx. Okay. Now my question to you at this point, do you want to just group these together and deal with these? Yes. Okay. Sine squared, another way to write squared would be 4/2, right? So sine to the 4/2 x times sine to the 1/2 x. Add the exponent. 4/2 minus 1/2 is 3/2. Or like Jordan did it. He said that would be 2 minus 1/2 is 1.5. So 1.5 x, so that's 3/2 x. Either way, we'll get it. Okay. Now, do you like to keep these like this, or do you like to split it into two different integers? I don't care. Second? Okay. All right. So let me go on and put parentheses around them then. Okay. Now are you ready for your substitution? Exactly. And what will you substitute? U equal which? Sine. You're absolutely right. Sine x. Perfect. Then du is equal to what? Cosine x dx. Perfect. And there's our cosine x dx. That's du. And this will be then, and we got one more thing to do here, and we'll do it in a minute. Let's just write the first things. What would that be? U to the negative 1/2 minus u to the 3/2 du. But what's the other thing we've got to do here? We didn't have to do it before because it was an indefinite integral. We need to change our limits because now our integration variable is u, not x. These are the limits for x. So go back up to our substitution. When x is equal to pi 6, what's sine x? What's sine of pi 6? 1/2. Perfect. So now the limit here will be 1/2. And sine of pi thirds, if you put that in here, put x equal pi thirds in here, put sine of pi thirds. square root of 3 over 2. That's going to go up top. The square root of 3 over 2. All right, now we're ready to integrate. Oh, what we've been waiting for. What is the antiderivative of u to the 1/2? Negative 1/2, sorry. U to the 1/2, say again?
U to the 1/2 over 1/2.
Over 1/2, which is the same as 2, right? Okay, minus, what's the antiderivative of u to the 3/2?
U to the 5/2.
5/2, yes, over 5/2, which is the same as times 2/5, right? When you divide by a fraction, invert and multiply by that same fraction. Because this wound up being a 1/2, flip that into 2. This is a 5/2, flip that into 2/5. Right? Follow? Okay. And what else? Oh! Evaluating this between square root of 3 over 2 to 1/2. Now these are the values for u, okay? Oh my word, how nasty. Okay. This is not going to be pretty, folks. It had been really pretty, hadn't it? Okay, when you put in the u here, which is root 3 over 2, that would be 2 times root 3 over 2 to the 1/2 power minus 2/5 root 3 over 2 to the 5/2 power minus, you have to do the putting in the second value, 2 times 1/2 to the 1/2 power. Ugh. Okay. Plus, because it's a minus, 2/5. I keep wanting to put the u in there. It's not a u, it's a 1/2. What's that? Wait just a second. Yeah. The sign is a positive because it's a minus, You use the minus of this, and that changes this. Say that one more time. Okay, you're not using signs anymore. You're just plugging u equal 1/2. Okay, no, the exponent is 5/2. It's 2/5, 1/2 to the 5/2. Now that is one ugly problem. I'm trying to think if there's any way to simplify that.
What is that second one there? You got 2 times the square root of 3 over 2 to the 1/2 minus. What is that one?
That's a 2/5. See, what I'm doing is plugging in to this thing, root 3 over 2. And for u, be 2 root 3 over 2 to the 1/2 power minus 2/5 root 3 over 2 to the 5/2 power. Then minus this one plugged in here, minus 2 times 1/2 to the 1/2 power, minus a minus, because it's down here, and a minus here, that would be plus 2/5, 1/2 to the 5/2 power. Sorry, I ran out of room over there. Now, yuck, how ugly. Is there anything to redeem this at all? I think I want to see, every one of these has a square root of 2 in the denominator. There's more than that, but there is at least the square root of 2 in the denominator. And they each have a 2 in the numerator. And 2 over root 2 would be root 2. Okay. So I'm real tempted to take out a root 2 up front. Okay. Because this is a 2 over the square root of 2. This is 2 over the square root of 2 raised to the 5th power. This is 2 over root 2. And this is 2 over root 2 to the 5th power. Okay? So, if you take out the root 2 from all those, and then you have this. Yeah, you can put it in the calculator. That's certainly true. Here's what they did. Oh my goodness, what did they do? They left the first one just like it was, and the second one just like it was, and the third one they just did minus root 2, which is what I was doing. And then the next one, I said, oh man, what did they do here? It's how in the world did they get that? 2/5. I know that's got to be there. Okay. And it's 1/2 to the 5 has power. That would be 1 over 2 to the 5 has power, which is be 1 over, that's it. Okay. I'm going to do it the way they did it, rather than the way I was starting to do it. Sorry, I have to go back to the top because I just run out of room at the bottom. So they left it just like this. 2 times the square root of 3 over 2 to the 1/2 power. That's their first term. Okay? Minus 2/5 times the square root of 3 over 2 to the 5 has power. Okay? Minus, now here's where they did this. It's 2 over the square root of 2, which is root 2. Okay? You see that's 1 over the square root of 2. Okay, that next one, here is the weird one. I'm going to write it out here, 2/5 times 1 over the square root of 2 to the 5th power. Okay? I took the 2/5, the 1 over root 2, I took the square root of that, and then left the 5 up top. Okay? Now that would be just this last one here. Let's just do this one. Okay? Because the rest, oops, yuck. Okay. Hit the wrong key here. Okay. Just that last term, because the other terms are just like they had. Okay. This will be 2 over 5, and this will be 1 over root 2 to the 5th power. Well, root 2 squared would be 2, right? Squared again, and root 2 squared again would be 2 again, times the square root of 2, right? 2, 4, 5. 5 powers there, okay? One of these 2's go out, and that leaves us with, let's rationalize that denominator and multiply it by root 2 over root 2. So this leaves us another 2 down here. So 5 times 4 is 20. So that would be root 2 over 20. They say root 32 over 80. Why in the world they ever came up with that, I don't know. Take out a 16 from the numerator, and that would be 4 times root 2, and 4 times 20 is 5. Yeah, that's what they get. Why they did 32 and 80, I don't know. But that would be the simpler answer. So everything else there plus root 2 over 20. Why they did root 32 over 80 is beyond me. So if you did all that and then use your calculator, you should get the same answer there. Wow. Okay, that was example 2. Okay, and we did it. Good for us. Okay. Now, they don't do example 3 either, so let's us do example 3. So I'm going to erase all my ink. Does anyone need that any longer? Okay. Erase that and let's do example 3. Find this one. The integral of cosine 4th x dx. All right. We don't have an odd power anywhere. In fact, we don't even have a sign in there. Okay. So, what are we going to have to do? Now, I'm going to point you backward a little ways. Let's go back a slide or 2, or 3 or 4. Ha! Okay? If you have an odd power, you use 1 or 2. If you don't have an odd power, when both of the powers of sine or cosine are even, or one don't even have and the other is even, and non-negative, then we're going to make use of these. Okay, remember those? That's from your double angle formula and your Pythagorean identity and double angle identity. Mix them together and that's what you get. Okay? Get to know them. You're going to use them a lot. Find them in your front or back of your book and know where to go and find them. They're there. They're there somewhere. But some of you don't have books. Okay. So those are the identities. And we're doing example 3, which is cosine. So we're going to be using that one. Okay? There it is. Okay? Now, we're going to rewrite this as the integral of cosine squared x squared dx. Okay? Right? And our identity that we had was what cosine squared was. And what was that?
So you would always get it to cosine squared x and then just put whatever you have left.
Whatever, yeah, exponent you need on the outside. So cosine squared x, again, is this one right here, 1 plus cosine 2x over 2. Okay. 1 plus cosine 2x over 2 squared dx. Okay? That means we've got to square the numerator and square the denominator, right? So that's the integral of squaring a binomial. I'll remember how to do that, right? Square the first, 1, twice the product, plus 2 cosine 2x, right? Square the last, plus cosine squared 2x over 4. you square the denominator as well. Right? And if it's okay with you, I'm going to go and take that 1/4 on the outside. Is that all right? Okay, let's do that. 1/4, and this is the indefinite integral, so we're going to have a plus c, remember, but we'll come back and mess with that later. Okay, now what do we have? The integral. 1, I can do that, plus 2 cosine 2x. Take me a little bit, but I can do that one. Okay, plus, SpaghettiOs. We have another square here. Well, guess what? We're going to use the same thing again. Cosine squared x, we're going to do is this. Only this time it's not cosine squared x, it's cosine squared 2x. So that's going to be, this is just that last term there. We pulled the 1/4 out. That last term is going to be 1 plus cosine this last term here. Use this formula here, 1 plus cosine 4x over 2. Do you see that? Yay or nay? This one just came down. We pulled the 1/4 out. This came down, that came down. We can do those. But we can't do that one until we do this again. Well, this thing squared, okay? This thing squared, it's going to be 1 plus cosine twice this, which would be 4x over 2. Okay? And I left off, and you should have corrected me, my dx here and my dx here. Okay. Now, don't especially care for that denominator. Okay? So I'm going to take out that 2, but in the process I've got to double these others, so this will be 1/8 the integral of 2 plus 4 cosine 2x, because I had to, if I'm taking out a 1/2, I have to double that numerator as well, plus 1 plus cosine 4x, if I could write, all that dx. Okay? Now, I don't really like that too much, so let's do the 1/8 out here, the integral. Let's combine these two terms and make it 3 plus 4 cosine 2x plus cosine 4x dx. Okay? And again, my question to you, do you want to split that into 3 integrals or just integrate that as it comes? I really don't care.
Just keep it together.
Okay, let's go with it like it is. Okay, so what's the antiderivative of 3? 3x. Right? Okay, plus antiderivative, now the 4 is just a coefficient, so we'll just leave it alone. Antiderivative of cosine 2x.
Be 4 negative sine 2x.
Okay. Are you taking derivative or taking antiderivative?
It would just be sine.
Huh?
It would just be sine. No negative.
Yeah, it will be sine, but is it plus or negative? That's my question.
Plus.
Plus, okay. Plus 4 sine 2x, except we got that 2x in there. So you have to undo the chain rule, which is dividing by 2. Remember, a chain rule, if you're taking a derivative, you multiply by 2. Antiderivative, you divide by 2. So that makes that a 2 then. This 2 here divides into the 4. Okay? Plus
Sine.
Okay, certainly it's going to have a sign. Give me a sign. I need a sign. Okay. It's going to be 4x. Chain rule in reverse.
Oh, so then you divide by 4?
Yes. I'm just going to put a 1/4 up front. And then ultimately a plus c because you're doing an indefinite integral. Okay, now if you don't like that other denominator in there, you could pull it out as well. So make this 1/32. But then that would be times 12x plus 8 sine 2x plus sine 4x plus c. That's one way to write it. To me, that's simplest because I don't like fractions that much. I know y'all love your fractions, but I don't really not care for them. Oh, they didn't quite do it that way, did they? Okay, they went back to the first way I had, or that top line there, and they did 3/8x plus, and 2 in the 8 would be sine 2x over 4 plus sine 4x over 32. So they left as many fractions as they could in there, plus c. Okay, which, same way. It's just whether you want all the fractions on the outside or all the fractions on the inside. It doesn't matter. Okay? Now.
So we divided that. We have 8 sine 2x. I thought we divided that 2 out.
Which one? We divided out this 2 into the 4 and gave us a 2 here. Okay? Now, what I was doing was bringing this 1/4 out here, which that will leave this, but it would be dividing out a 1/4 is multiplying by 4, so that made that an 8 and made that a 12. Okay, multiply it back the other way. What's common between these two? 4. That'd be 3x over 8 plus 1x over 4.
But it's that 2x right there. That's how we divided out.
Okay, this 2x? No, that's part of your argument. You can't. You don't mess with that. Don't mess with that. This says 4x. You don't mess with that. That's the argument of the sign.
Okay.
What you divided out was the coefficient. I think both of those give the same answer. Let me check again and make sure. Yeah. Sine 2x over 4 and sine 4x over 32 plus c. Now, this is a massive illustration of why I do not like WebAssign. Do any of you really love WebAssign? You don't. Oh, okay. And here's why. Only one answer is ever recognized by WebAssign. And I can think of 3 or 4 perfectly good answers, ways to write that answer. The book did it one way, I did it another way. They're both absolutely correct. WebAssign's going to count one of those wrong and tell you you got a wrong answer. And then you think, oh, I did the problem wrong. No, you didn't. You did the problem perfectly right. Your answer's perfectly correct. It's just that WebAssign's looking for a different form for that. Especially when you get calculus, my word, you can express your answer in so many different ways that are all equivalent. And so I just do not see how WebAssign ever works for calculus. Oh, and something I've been supposed to do for my first class, I completely forgot. So I'm going to do it for this class now. Do any of you know Miss Nyla Gerasi? Okay. She is really wanting you folks on the math team. Now, Clark has done it before, and it sort of was fun, wasn't it?
It was fun. I just didn't really have time to
right.
think about work a lot.
And I hope you don't mind this. Clark, when he was in, I think it was Cal 1 when you did it before, wasn't it? he was so hesitant to ever say anything. He was on the math team for a few weeks, and soon he was answering questions before I could get him out, because he had learned that in math team. And did you get that same impression?
Yes, sir.
Yeah. It really helps. It really, really does. Okay? I can't remember the day she meets with them, but I think she has all of you on her list, doesn't she? There is the Blackboard class for the for the math team. Check it out, folks, please. You'll have a lot of fun, and you'll learn a lot of math. You'll learn shortcuts that the book never tells you, and I won't necessarily think of telling you. It really is a very helpful thing for later on when you're in higher level courses. You can zip through the stuff much, much faster. Please give it a shot. Okay? I think you'll find it quite enjoyable. So, think about it. All right, that was example 3 in several different ways. Okay? Now, whenever you're doing these antiderivatives, if you're not certain about it, just take a derivative as soon as you get the same thing. Okay? I don't know. I saw it earlier. I'm trying to think now. Oh, yeah, when we were doing this. When we were going from this when we were integrating this and going to this, okay? We'll take the derivative of this, you get 3/8. First term here is 3/8. Take the derivative of this will be 1/4, right? 2/8. 1/4 sine 2x. That would be 1/4. The derivative of sine 2x would be cosine 2x times 2. So that would be 1/2, and sure enough, this is 1/2 cosine 2x. So if you go back and do the derivatives of them, if you're not certain you did the antiderivative right, just take a derivative of it and see if you don't get back the same thing you did. And I think you'll find you do. Every time. Or you made a mistake. Okay, one or the other. Okay. Any questions on that? All right, let's go to Wallace's formula. Oh, wait. Let's go back again. Whoops. Yeah. So in example 3, when you evaluate the definite integral from 0 to pi halves, you obtain, so let's do the same thing, but we're going to go from 0 to pi halves. Okay? So let's see what we get. This will be this thing evaluated from 0 to pi halves. All right. So 12 times pi halves would be 6 pi times 32. Goodness gracious, what an ugly, messy thing. Why would they want to do this? Okay. So 6 pi over 32 would be 3 pi over 16, I think. Yeah. Okay. Plus, well, if you double pi halves, you get pi, and the sine of pi is 0. So that one goes away. And if you multiply 4 times pi halves, you get 2 pi. Sine of 2 pi is 0. So that goes away. And then subtract off from this, so we'll make that a minus sign. 0, well, that goes to 0. That goes to 0. That goes to 0. You get 3/16 pi, and that's exactly what they got there. Okay. Ooh. That doesn't mean that's got to be the right answer, it says, note that the only term that contributes to the solution is the 3/8x. Okay. Now, that observation led John Wallace. Now, I'm trying to remember if he was the Lucasian Chair of Mathematics at Cambridge before, when he got Newton as a student, I think he gave over the chairmanship to Newton because he was such a brilliant guy. So he was actually an instructor or a professor who helped Newton and also Leibniz out. He influenced the thinking of both of those men. He is credited with introducing the present symbol infinity, okay? Another of Wallace's contributions. And you can see more about Wallace at larsoncalculus.com. This observation is generalized in the following formulas developed by John Wallace, who lived 1616 to 1703. And 1616 was well before either of those two gentlemen were born, and they came to prominence in his midlife, you might say. So here's, if n is odd and greater than or equal to 3, so it doesn't work for n equal 1, okay, then the integral from 0 to pi halves. Now this only works from 0 to pi halves. Cosine to the nth x, okay? Well, here's what you do. You start with 2/3. You don't say why, but start with 2/3. And then each of these is increased by 2. 2/3 times 4/5 times 6/7. Notice you're increasing each of these by 2. And until you get to n minus 1 over n. Okay? So the next one would be 8/9, 10, 11. So you keep on going until you reach that end. Now, we didn't do any with cosine, did we? Or did we? Yeah, the one we did was 4. Yeah, that was it. Okay? But this is n is odd. Now, if n is even, which is what we had, n greater than or equal to 2, we had is 4. That's the one we did. Then you do 1/2 times 3/4 times 5/6. Keep going until you get n minus 1 over n. Well, here's your n minus 1. We had a 4 here, so it would be 3/4. So we stop right there. So this, there, times pi halves. Okay? If it's cosine, you don't multiply it by any power of pi. But if it's even, then you do multiply. If it's odd, you don't multiply by power of pi, but even you do. Okay? And then this gives you these two multiplied by pi halves. 3 pi over 16. And that's exactly what we have. That's only when your limits are 0. Okay. Now let's make sure. Yep. They did it right. And it says these formulas are also valid when cosine nx is replaced by sine nx. You're asked to prove both those formulas in exercise 87, if you choose. Okay. All right. Does anyone realize, well, we won't go into that. Let's move on. Okay. All right. Ready to move on. Okay, and remind me, this class goes until 2:10, which we just have reached, haven't we? Sorry about that, folks. We will pick up next time with integrals involving powers of secant and tangent. Okay? So that will be on page 8.3. Now, before you go, let me give you a few homework exercises. You can do any of the odds, 3 through 13. They're all at calcchat.com. 7's at CalcView as well. You can do any of the odds 15 through 19. They're all at CalcChat. And those use Wallace's formula. So we'll stop there, so go through 19. Good deal. Any questions?
We're out next Monday, right?
What's that?
We're out this coming Monday.
Yes, but we'll be here Wednesday. Okay. Good deal.
We have a good one.
You too. Thank you.
Oh yeah. How did the surgery